Today we're going to be learning about graphing by finding points, particularly finding intercepts, and how to solve linear equations and linear inequalities. We will also be learning about how to use interval notation more broadly. If there is a particular topic that you want to be sure to do, I would highly recommend that you look at the timestamps in this video. All algebra videos have been made such that they have timestamps. But without further ado, let's go ahead and get started. So the first topic of this video is how to graph using coordinates on the coordinate plane, in particular intercepts. And that can be found in section 2.1 of your textbook. As hopefully a review, remember that the coordinate plane consists of two axes. We have the x-axis that goes left to right, and we have the y-axis that goes up and down. Always remember which one's which, and that the x has these two little feet that allow him to run left to right, while the y only has one leg that allows him only to jump up and down. All points are listed as x and then y, namely that you have to move left and right before you're allowed to climb up and down to something. So if you want to climb a tree, you have to run over to the tree before you can climb up it. If, for example, you have the point 2, -1, that means that you want to move right 2 and then down 1, because it gives you first the x-coordinate and then the y-coordinate. Similarly, just as a reminder as well, the x's, the right is positive, the left is negative, and on the y's, up is positive and down is negative. The way we label the parts of the coordinate plane is that we label it in a counterclockwise fashion, where we start with quadrant 1, where both x's and y's are positive, then quadrant 2, where x's are negative but y's are positive, then quadrant 3, where both x's and y's are negative, and then quadrant 4, where x's are positive but y's are negative. This in particular, in this counterclockwise motion, becomes very handy in pre-calculus. We do a little bit with it in this course, but that is more something that you will see often show up in that class. Again, as a reminder, to plot points, it is always x and then y. So for example, the point 3, -1 means you move right 3 and then down 1 for the point 3, -1. I want you to go ahead and pause the video and try to plot these 3 points. Even if you don't have graph paper available, go ahead and just sketch it out on a piece of paper. Welcome back. Let's go ahead and plot these points together. So for the point -2, 4, that means I move left 2 on the x's and then up 4 on the y's for the point -2, 4. For 3, 3, that means I move right 3 and then up 3. And then for the point 0, -3, don't get thrown off by the 0. That just means I'm not moving left and right at all, and I just move down 3. This type of point also has a special name. It is known as a y-intercept. If you notice on a y-intercept, that means x is 0 because I physically cross the y-axis. You can always graph any particular equation by simply plotting enough points. How many points you need to plot depends on the type of equation we're talking about. With linear equations, we're talking about a minimum of 2. Linear equations being the type of equation we're going over today, which is where you have maybe something times an x plus another number, something like 2x - 3, or maybe just a -1x without anything being added, or even technically just a 4 where you don't have an x and it's just always 4. Any of those are sorts of linear equations. The way that you actually can graph these, although there are other methods, is literally just plug and chug some points. So let's see what that looks like in practice. So if, for example, I have y equals 2x - 1, well, I want to remember what this actually means. That means 2 times x - 1. If you just see a 2x like that, there is secretly multiplication right there in between. All other operations really are explicitly shown, such as 2 plus x, x - 2, x divided by 2. All of those are really explicit. But for something like multiplication, we just tend to write 2x instead. And that is just a quick reminder of that notation. So in order to graph this by plotting points, what we're going to do is just pick some x's. These are ones I happen to pick. You could pick anything that you wanted, but I'd recommend being nice to yourself and picking something that's fairly simple in a relative sense to plug in. While you could plug in -300, 200, 427, whatever it is that you want. Nice small integers are typically the best to plug in, just for your own sanity. So if I plug in -3, for example, that means I replace everywhere I see an x with that -3. So that becomes 2 times -3 minus 1. Order of operations, I do that multiplication first. 2 times -3 gets me -6, minus 1 gets me -7. So I just figured out that the coordinate -3, -7 exists on this plot. Now this is a little bit off the page, so to speak, because I would have to go over to -3 and down to -7. It would be roughly somewhere down here. So if I was on a test or something, I would want to find a different x value that I could plot more precisely if I was just given and limited to this coordinate plane here. But keep in mind that point -3, -7 does still exist. It's just a little bit off of this given plot that we have here. So let's try some other points. If I plug in -2, that would be 2 times -2 minus 1. 2 times -2 gets me -4, minus a 1 gets me -5. So I know I have the point -2, -5. Now I'm actually on the page because I go over to -2 on the x's, down to -5 on the y's for the point -2, -5. Go ahead and pause the video and try to find these other points. Welcome back. Let's go ahead and go through these other points real quick. So if we have 2 times -1 minus 1, 2 times -1 is -2, minus 1 gets me -3. So I have the point -1, -3 that I can go ahead and plot. If I plug in 0, well, anything times 0 is 0, so I have 2 times 0 is 0, minus 1 is -1. So I also have the point 0, -1. That also happens to be a y-intercept, which if you knew anything about slope-intercept form, which is something that we will be going over later, you might have predicted that -1 should have been our y-intercept. If you don't remember that, no worries, we'll be going over it in a few lessons. If I plug in 1, then that becomes 2 times 1 minus 1. 2 times 1 is 2, minus 1 gives me +1. So I have the point 1, 1. If I plug in +2, well, 2 times +2 is 4, minus 1 gets me 3. So I have the point 2, 3. And if I plug in, last but not least, but +3, well, 2 times +3 is +6, minus 1 gets me 5. So I have the point 3, 5. And this was honestly more points than I necessarily needed to plot, but it does show you that nice, beautiful linear pattern. Again, you need a minimum of 2 anytime you're creating an equation. I would honestly recommend 3 though, just to make sure that if you make a silly arithmetic mistake, you haven't completely thrown off your graph. Go ahead and try this next one yourself. If you need a hint on how to get started, remember that this -x secretly means -1x, which is really -1 times x and then adding a 2. All right, welcome back. Let's go ahead and go through this together. So if I plug in -3, that's -1 times -3 plus 2. -1 times -3 gets me +3 plus 2 is 5. So that's the point -3, 5. If I plug in -2, -2 times -1 gets me +2 plus 2 is 4. So I have the point -2, 4. We can go ahead and plot those. If you notice, this will be facing the opposite direction. That's because it has a negative slope, which is something we will go over more formally later. If we have -1 times -1 plus 2, that gets me -1 times -1 is 1 plus 2 is 3. -1, 3. If I plug in 0, well, even a negative times 0 is still 0, so 0 plus 2 gets me 2. Have the point 0, 2, and that is again a y-intercept. If I plug in 1, -1 times 1 is -1 plus 2 is +1, so this graph also happens to have the point 1, 1. If I plug in +2, well, -1 times +2 is -2 plus 2 is 0. So here, because it physically crosses the x-axis, that is considered an x-intercept. So that exists at a point where I have some x value, but I haven't moved up and down. So my y is equal to 0 on an x-intercept, and on my y-intercept, I have 0, a y value, where now my x is equal to 0. At first, that might seem backwards whenever you're doing the algebra, but just keep in mind the physical picture. If I cross the y-axis, I haven't moved left and right. That means x is 0. If I cross the x-axis, I haven't moved up and down. That means y is 0. And last but not least, if I plug in +3, well, -1 times +3 is -3 plus 2 is -1. So I have a point here at +3, -1. And then I can connect these guys, and you have a nice, beautiful line. Intercepts are oftentimes special points that we in particular want to find. So for an x-intercept, again, that means you plug in y is 0, and for a y-intercept, that means you plug in x is 0. And that's exactly how you find these intercepts. So you can graph equations by just knowing 2 points, and intercepts are often the nicest points to find. If I want to find an x-intercept, what does that mean I do again? Ask yourself and pause the video. That means that I plug in y is equal to 0 because I have not moved up and down. So in the equation y equals negative 3x minus 4, I replace y with a 0, and now I want to solve for x. We're going to go over the solving more formally here just in the next section, but let's go ahead and hopefully this is something relatively familiar to you. That I want to undo any addition subtraction first, so I want to undo subtracting 4 by adding 4 to both sides. So I add 4 to both sides, I get 4 equals negative 3x, and that is my last step. Remember that negative 3x means secretly negative 3 times x, so I get rid of multiplying by negative 3 by dividing by negative 3. So when I was undoing subtracting 4 by adding 4, I really made 0. I made negative 3x plus 0. And whenever I undo multiplying by negative 3 by dividing by 3, I'm really making 1. So this is really now that I just have a positive 1x is equal to negative 4/3. So I just figured out the point negative 4/3, comma 0 exists on this graph because I found it by plugging in y is 0. Don't freak out just because it's a fraction. If I have the fraction negative 4/3, well, that is just slightly more negative than negative 3/3, and negative 3/3 is equal to negative 1. So I have a point here in between negative 2 and negative 1, slightly closer to the negative 1. If I want to find a y-intercept, that's usually actually somewhat simpler math, most times, not always, but most times it is. So if I have y equals negative 3x minus 4 to find the y-intercept, now what do I do? Pause the video and ask yourself. That means I plug in x is 0. So I'm going to plug in x is 0, and this is why a lot of times the arithmetic is kind of nice, because anything times 0 is 0. I'm just left with y equals negative 4. So I know I have a y-intercept at the point 0, comma negative 4. And then I can just connect those guys. Go ahead and try this next one on your own before we go over it together. So if I want to find an x-intercept, remember that means that I want to plug in y is equal to 0. So I do 0 is equal to negative 3/4 x plus 3. I still want to undo any addition subtraction first, so I'm going to subtract 3 from both sides. That cancels out to make 0. I'm left with negative 3 is equal to negative 3/4 x. And then there's 2 different ways you can go about it from here if you're not as familiar with working with fractions. I'm going to call it way A, is actually that you just deal with a fraction directly. So if I have negative 3 is equal to negative 3/4 x, remember that negative 3/4 is simply a number, so I'm still allowed to divide by that number. Negative 3/4 divided by negative 3/4 is indeed still 1. That's what I mean when I cancel it out there. And then for negative 3 divided by negative 3/4, well, remember that a number divided by the fraction is the same thing as doing the number multiplied by the fraction's reciprocal. You might have heard this in the past as keep, change, flip. And whenever I do negative 3 is secretly divided by 1. Multiply across the top, negative 3 times negative 4 is positive 12. 1 times 3 is 3. That just becomes positive 4. So that is one way to get that x is equal to positive 4. Another way, I'll call it way B, is that you can treat this like a 2-step equation. So if I have negative 3 is equal to negative 3/4 x, well, the first thing I could undo is dividing by 4. So I can multiply both sides by 4. That cancels out to make 1. 4 times negative 3 is negative 12 is equal to negative 3x. Then I want to undo multiplying by negative 3 by dividing by negative 3. Negative 3 divided by negative 3 is 1. Negative 12 divided by negative 3 gets me positive 4, which if you'll notice, that's really just I did a 2-step way of exactly this multiplying by the reciprocal process. And that's just a way to keep yourself straight if you're not as comfortable with fractions. And that gives us the point positive 4, comma 0. I can go ahead and plot that on the graph. And then for the y-intercept, what we do there is plug in x is equal to 0. So y equals negative 3/4 times 0 plus 3. Even a fraction times 0 is still 0, so we're just left with y is equal to positive 3. So I have the point 0, 3. And then I can just go ahead and connect those guys. It's okay if your line's not perfectly straight like mine. If you're doing things on ALEKS, they'll make it straight for you. And if you're doing it on a test, that's why you show your work. Your professor would be able to know what you mean by this. As we touched on a little bit, we end up having to solve linear equations all the time in this class. We're also going to solve lots of other types of equations, but linear equations are really the backbone of what we do. And a linear equation, again, is any time I have just a number times x plus another number. So I'm not dealing with any exponents on the x. I'm not dealing with x's being in the denominator of a fraction. I'm not dealing with like a number to the x power. I'm not dealing with any square roots of x, nothing like that. I'm just dealing with like 3x minus 2. It could even be a funky number like 3/4 x minus 2/3, whatever it might be. Could be that I'm adding zeros, so you just have something like 2x. Could be that I'm doing 0 times x, so you just have something like negative 3. Anything like that is considered a linear equation. And then you'd set them equal to some other number, whatever it might be. Well, if I'm doing negative 3, that has to be equal to itself. It's going to be a true statement. So how do you solve linear equations? So this is sort of the long and formal way of saying it, but in short, as long as you do things to both sides, we're okay. But just make sure that you never divide by 0. That's a big, big no. But you can add, subtract, multiply, divide, whatever it is, as long as you do it to both sides, you're good. Sometimes it is helpful to apply the distributive property. Because if you have a times something in parentheses, that really means that you can just distribute across those parentheses and keep that addition there in the middle. And the goal, again, is to isolate a variable on one side of the equation. The shorthand of how I would think of these steps is if you have a two-step equation like this, you really want to be thinking first you want to undo addition and subtraction, and then you want to undo multiplication and division. We'll add on a few more steps for more than two-step equations like this, but if you just have something that's already kind of written in this linear form like we were talking about earlier, undo addition, subtraction, then undo multiplication, division. So for example, on this first equation, 2x plus 1 equals negative 9, what do I want to undo first? I want to undo adding 1 by subtracting 1 to both sides. That means this cancels out to make a 0. You always want to think about what that slash mark really means, because we use cancel out all the time. That means positive 1 minus 1 makes 0. So I've got nothing else being added now. I'm left with 2x is equal to negative 9 minus 1 gives me negative 10. That is my next step. I'm going to say, okay, well, 2x, I know that's really 2 times x. How do I undo multiplying by 2? I divide by 2, because now I'm really saying 2 divided by 2 makes 1. So I'm left with a single x. Negative 10 divided by 2 makes negative 5. It's always worth, especially on a test, to double check your work. I'm not going to show that step every time, but I'll show it to you once, where you just basically plug this into this equation just like we did earlier. Because it should be that 2 times negative 5 plus 1 should give me negative 9. 2 times negative 5 gives me negative 10 plus 1 does indeed give me negative 9, so I know I solved the equation right. Go ahead and try this next equation yourself, and I would really encourage you to make sure that you're dealing with this fraction without a calculator if possible, since that is good practice. Welcome back. Let's go ahead and go through how to solve this equation. So if I'm thinking about my steps, I want to first undo adding 1. So I will undo adding 1 by subtracting 1 to both sides. I'm left with 2/3 x is equal to negative 10. Then I'm going to personally undo that 2/3 in the two-step way. So I'm going to undo dividing by 3 first by multiplying by 3. So you're really saying 3 divided by 3 is 1. And when I do things to one side, I have to do them to the other. So I'm left with 2x is equal to negative 30. Then I want to ask myself, how do I undo multiplying by 2? Well, now I divide by 2. 2 divided by 2 makes 1. I'm left with x is equal to negative 15. Now, if you have a few more things going on in your equation. Don't freak out, it just changes those initial steps a little bit. So the first thing you want to do is deal with those parentheses. You don't have to deal with parentheses by distributing, strictly speaking. There are other methods, but it is the method that will always work. So if you just want something that will work every time, I highly recommend just dealing with distribution first. So distribute if there are parentheses. And that includes if you just have a minus parentheses. If you have just like a minus parentheses, you're secretly distributing multiplying by -1. Then I would personally recommend combine like terms within one side of the equation. So there you're not undoing anything, you're just combining like terms. Then you want to move all x's to one side. And then once you do that, if you do all three of those steps, you will be in an equation that looks like those previous two that we just had, where then you will just want to undo addition and subtraction, then undo multiplication and division. So let's keep that in mind. And sometimes with really long equations like this, I like to make sure that I'm keeping my sides of the equation straight. So I'm actually going to just like write a line for myself down the middle of like what's on which side of the equation. You don't have to do that, but I find sometimes it will be helpful in order to keep track of what's on what side. So first, let's do our first step. So first we want to distribute if there are parentheses. In this case, we do have that. So we first distribute 4 times x gets me 4x. 4 times -3 gets me -12, and then I just drop down the other term. Equals, here that 15 is not being distributed, so I'm just going to drop them down. And when I'm distributing this 5, keep in mind this negative is attached to them. So -5 times x gives me -5x. -5 times 6 gets me -30. And now I've done that distribution step. Now I want to combine like terms within one side of an equation. So again, we're not undoing anything at this step. Here I'm just saying if this was a phrase over here that I was just told to simplify, what like terms do I have? Well, I have the like terms of -12 and +12. -12 plus +12 gives me 0. So that's really 4x plus 0 on that side. And typically we don't write plus 0. So it's really just 4x. And similarly, on this other side, I have a +15 and a -30 that are like terms. +15 plus -30 gets me -15, and then I also want to drop down that -5x. And now I have combined like terms. Next, I want to move all x's to one side of the equation. Technically, it doesn't matter which side you pick, but if I'm trying to, think ahead here, well, on this left-hand side, I just have a 4x, while on the right-hand side, I have both a -5x and a -15. So I'm thinking that on the left-hand side, this is already prime real estate for just x's, so I'm going to get rid of adding -5x by adding +5x, because -5x plus +5x makes 0. You always again want to ask yourself, did I just make 0 or did I just make 1? You should be making one or the other if you're canceling things out, quote unquote. 4x plus 5x gets me 9x is equal to -15. We don't actually have any undoing of addition subtraction here, so I can ignore that step. And then now I just want to undo multiplication division. Well, the x is being multiplied by +9, so I undo multiplying by +9 by dividing by +9. 9 divided by 9 makes 1, so I'm left with x is -15 over 9. Then I want to ask myself, is there anything that goes in to both -15 and 9, meaning do they have a greatest common factor? In this case, 3 goes into both, so x is really equal to -5 over 3. I want you to go ahead and pause your video and try to solve this yourself. Again, if you find yourself having trouble keeping track of what's on what side of the equation, I just recommend drawing a line down the middle like that. I won't do that every time, but I'll do that for the sake of this video. Welcome back. Let's go ahead and solve this. So first things we want to do is distribute this guy. So negative 2 times 3x gets me negative 6x. Negative 2 times negative 1 gets me positive 2. I just want to drop down the x. Equals 14 minus x. I didn't distribute over here, so I'm just dropping them down. Then I want to ask myself, are there any like terms here? So I noticed that negative 6x and positive x are considered like terms. Negative 6x plus positive 1x gets me negative 5x. And then I'm just going to drop down everything else. Don't try to do too many steps at once. Use as much space as you need. And that's another place that people will mess up a lot, is if you try to do too much at once, you're apt to get something confused. You're apt to mismatch something. Just do one step at a time. That's totally fine. Then I want to move all x's to one side. Here, there's not necessarily an obvious candidate for which side. I like to keep my x's positive if I can, so I'm just going to add 5x to both sides to get rid of adding negative 5x. Negative 5x plus positive 5x makes 0. And I'm left with 2 is equal to 14. Negative 1x plus 5x is positive 4x. Now I want to undo any addition subtraction. So right now this 14 is being added to my 4x, so I want to undo adding positive 14 by subtracting positive 14. That cancels out to make 0. I'm left with negative 12 is equal to positive 4x. As my last step, I want to undo any multiplication, and 4x is 4 times x, so I want to undo multiplying by 4 by dividing by 4. 4 divided by 4 makes 1. And I am left with x is equal to negative 12 divided by 4 is negative 3. We're going to be talking about this concept of domain very often in this class. And what domain just means is, what am I allowed to plug into the function? What's possible input? And if I have something like 2x plus 3, are there any numbers in existence that I'm not allowed to plug in? There's actually not. So I'm good. We can plug in any number we want. We could plug in fractions, we could plug in 0, we could plug in negatives, we could plug in positives. So this is actually all real numbers. Or a fancy way of saying that is negative infinity to infinity. Now you might be asking yourself, well, isn't that always true? Not necessarily. If I had something like y is equal to 1 over x, what number would I not be allowed to plug in? I would not be allowed to plug in 0 because I'm not allowed to divide by 0. What if I had something like y is equal to the square root of x? What would I not be able to plug in? I could not plug in negative numbers if I'm going to stay real. If I have a negative underneath a square root, that's imaginary. That's like in the last part of this class, so this x has to be positive. And in terms of issues in domain algebraically, until we learn about logs, those will be kind of the two big things. And this is really something that will be in a future lesson, but I want to kind of plant that seed in your brain. For now, what you really need to worry about is that I'm allowed to plug in anything to a linear function. That's okay. And then I want you to have kind of in the back of your mind that whenever we get to chapter 3, I want to be thinking about, are there any x's in the denominator? Those can't be 0. Are there any x's underneath something like a square root? Then x has to be positive. Last but not least in this section, let's talk about linear inequalities. So if it's a linear inequality, basically all I did was replace that equal sign with something like a greater than or equal or less than or equal. Let's actually go into what some of this notation means though. Remember that if I'm facing this way, something like x is greater than 0, that is read as whatever is, I eat the bigger number and point to the smaller number, I read it left to right as x is greater than 0. Greater than 0. If I have something like this, x is less than or equal to 0, now I'm pointing the opposite direction. I point to the smaller number, I eat the bigger number, and this line underneath means I'm allowed to be equal to. So that is x is less than or equal to 0. Let's go over that a little bit more formally, so to speak. So if there's a couple different ways I could have x being trapped in between two numbers, and it basically just depends, do I include these endpoints or not? So if I shade in the circle, which corresponds to having a line underneath that inequality, that means those numbers are included. So if, for example, I had negative 3 is less than or equal to x is less than or equal to 2, That would mean A in this case is -3, B in this case is 2, and I'm allowed to be any number in between and including. That would mean that I'm allowed to equal -3, I'm allowed to equal 0, I'm allowed to equal 1, I'm allowed to equal 2, but I couldn't equal something smaller like -10, and I couldn't equal something bigger like 5. The way we indicate this in interval notation, which is a notation we'll use all the time in this class, is the same order of the number line. So you do a -3, 2 in this case, and then we use square brackets to indicate I'm allowed to equal that number. If, for example, I had the same thing, but I was only allowed to equal the 3 and not the 2, well, then I use a closed circle on the 3, but I use an open circle on the 2, and that means I'm allowed to get really, 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 really close to 2. Oh, -3, my bad. That's to the left of it, that better be negative numbers. So I'm allowed to get really, 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 really close to 2, something like 1.99999999, but I can't equal 2 itself. And the way that we indicate that in interval notation is I use a square bracket on the -3 to say I can equal -3 itself, but then I use a parenthesis on the 2 to say I get really, really close to 2, but I can't quite touch it. Now, what if there is no upper bound or is no lower bound? So if I wanted to say all numbers strictly bigger than -3, for example, that means I use an open circle on the -3 and I just shade everything to the right and then kind of do a little arrow at the end to indicate keep on going all the way to positive infinity. No matter what, regardless if I include that lower bound or not, I'm going to use a parenthesis on infinity or negative infinity always. And that's to say that philosophically we never actually reach infinity or negative infinity. We just are approaching the idea. It's more kind of a math philosophy thing, but kind of the short of it is that you need to know that you never, ever, 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 ever put a bracket on an infinity or a negative infinity. That is always a parenthesis. And we always, to the left, are approaching negative infinity, and to the right, we're approaching positive infinity. So let's translate some of these words into inequalities. And everywhere I see like all real numbers or something, think of that as some sort of variable I'm going to represent that with as a placeholder. So if I want to do all real numbers greater than or equal to -2, go ahead and pause this video and try to make the inequality, the graph, and the interval notation for that. Welcome back. Let's go ahead and go through that. So if I'm doing this in inequality, so that would be x is greater than or equal to -2, reading it left to right. That means on a number line, I put a -2. Since it's allowed to be equal, I'm going to do a closed circle. And for greater than, I'm going to approach positive infinity over here to the right. If I want to translate that to interval notation, now that I've made my number line, it's in the same order. So I'm going to do a bracket on the -2 to say I'm allowed to equal the -2, comma, positive infinity, and use a parenthesis on that upper bound. What about all real numbers in between -3 and 5? Go ahead and try to do this yourself as well. So if I'm in between -3 and 5, this is actually a case where I find the number line and interval notation to be faster to do first, and then I'll do the inequality notation. So that means -3 is my lower bound, 5 is my upper bound. Whether or not we include them, I would argue maybe is slightly ambiguous, but since it just says strictly between, we actually in a math sense say that means that we don't include those numbers itself. If you did close circles there, though, don't beat yourself up. That's kind of a little bit of a trickier one, and probably not the type of thing we would emphasize on a test. But technically it is just supposed to be strictly in between, not those numbers included. And then we just shade right there in between. So for that interval notation, that's just -3, 5, and it'll be a parenthesis on both because I am not allowed to equal either. Now for the interval notation, I'm going to similarly put x in between -3 and 5, and now I want to think through what those symbols will be. So x is smaller than 5, and -3 is smaller than x. So that is why those face that direction, and that is always the direction that you'll have them face. If you had instead said x is bigger than -3 and x is smaller than 5, that would also be true. So sometimes people write and statements as this three-sided inequality, and sometimes they physically put the word and in between. Last but not least, all real numbers less than or equal to -1 or greater than 1. Go ahead and try this yourself. All right, welcome back. So let's go ahead and go through this. So this is x is less than or equal to -1, or x is greater than 1. So to indicate an or statement, you just literally write the word or in between. And that means just one or the other has to be true. For this and statement, it had to be numbers where both it was bigger than -3 and smaller than 5. Here, it's okay if just one or the other is true. In fact, it's only possible for one or the other to be true, because if I am less than or equal to -1, I cannot physically be greater than 1. So if this was an and statement, it just wouldn't work. If I'm going to translate this to interval notation, well, over here on the number line is negative infinity, over here on the number line is positive infinity, and then I go in the exact same order. So I do negative infinity to -1 inclusive, because it was allowed to equal -1. And then I use this little funky U, this union for or. And then I do 1 to infinity with a parenthesis on the 1 because it is an open circle. When it comes to solving linear inequalities, it's the exact same as solving linear equations, with one big caveat, that if you ever multiply or divide by a negative, you must flip the inequality. And while you can technically solve for x on either side, I recommend keeping x's to the left, just because we read left to right and it's going to make it easier to read your inequality. Because, for example, x is less than 3 is the same thing as 3 is bigger than x. But this one is a lot easier to translate into a number line, in my opinion. Now, if you feel equally comfortable with both, they're both correct, don't get me wrong, but usually it is easier to solve for x on the left, and that's what I'm going to show you. And this is, again, just reminding you that if you ever multiply or divide both sides of the inequality by a negative, and that means by a negative. So if I have -3x is greater than 2 divided by -3, that's whenever I have to flip the inequality. -2/3. My bad. I almost wrote that backwards. But if I have something like 3x is greater than -2, and I'm dividing by 3, it's okay that this is a -2 divided by a positive. That you keep the inequality facing the same way. It's only when you are actually doing this operation to both sides, where the thing you're doing to both sides is multiplying or dividing by a negative, then you flip the inequality. So let's go through this. So first things first, we want to move all x's to one side. If we had any parentheses, we would deal with that first, actually, but we don't. So we want to move all x's to one side, and while you technically can pick either side, you really want to move your x's to the left, just because it's going to make your inequality easier to read. So I want to undo adding +10 by subtracting +10. 10 minus 10 gives 10x minus 10x, and gives me 0 x's. I'm left with 13 minus 17x is greater than or equal to -4. Then I want to undo any addition subtraction. So the way I undo adding +13 is subtracting +13. 13 minus 13 makes 0. I'm left with -17x is greater than or equal to -17. And as my last step, I want to undo multiplying by -17 by dividing by -17. So here, since I'm dividing by a negative, that cancels out to make 1, and now I need to flip my inequality because I divide by a negative, and then -17 divided by -17 is still just 1. If I'm talking about the interval notation, it's probably helpful to put this on a number line, so since it's allowed to equal, I'm going to do a closed circle, and I'm going to shade to the left. If you also notice, the inequality points to the direction in which you shade. That's another way to kind of keep that straight as well. And now this goes from negative infinity to +1 with a bracket on that +1. So the way the interval notation is always the same order as the number line. Go ahead and try this next inequality yourself, and then we'll go over it. All right, welcome back. Let's go ahead and solve this inequality together. So first things we want to do is move all x's to one side. So I'm going to subtract 1/2 x from both sides. 1/2 x minus 1/2 x makes 0. -x minus 1/2 x gives me -3/2 x. Add 4 is less than 1. Then we want to undo any addition subtraction, so I'm going to subtract 4 from both sides. 4 minus 4 makes 0. I'm left with -3/2 x is less than -3. I'm going to personally then solve this in the two-step way, where first I will undo dividing by 2 by multiplying by 2. Here's how just multiplying by a +2 No need to flip the inequality just yet. I have negative 3x is less than negative 6. Then I want to undo multiplying by negative 3 by dividing by negative 3. Negative 3 divided by negative 3 makes 1, so x is greater than 2. And if I'm putting this on a number line, open circle on the 2, shade now to the right, and that is 2 comma infinity, to go in the same order with a parenthesis on the 2 because it cannot equal. If you have a compound inequality, that just means that you want to do that operation to all three sides. If it was a compound inequality that was an or statement, you would just solve them separately, just like we did here. So if, for example, I had just stuck the word or in here, then I would just have both of these be relevant solutions. That's not the case, but or just treat it like it's kind of like two separate problems and then you stick a union in between. Here, if this is an and statement like here, if it's given to you in this format, you want to just solve on all three sides of the inequality. So here, first things first, in order to get this x by itself here in the middle, is I want to undo addition subtraction by subtracting 2 to all three sides in order to keep it balanced. 2 minus 2 makes 0, 3 minus 2 makes 1, is less than or equal to 2x, which is less than 6 minus 2 is 4. Last step, I want to undo multiplying by a positive 2 this time, so I'm going to divide by positive 2. 2 divided by 2 makes 1, so I have 1/2 is less than or equal to x, which is less than 2. And now this is the same order I added on the number line, so I have 1/2 here, I have 2 here, the 1/2 gets a closed circle because it's allowed to equal, the 2 gets an open circle because it's not allowed to equal, and x is physically in between. Reading this left and right, 1/2 is less than or equal to x, which means x is bigger, and x is less than 2, so x is smaller. So their overlap is right here in between. Go ahead and solve this next one yourself, and then restart the video to see how you did. All right, welcome back. Let's go ahead and get x by itself here. So we want to add 8 to all three sides to undo subtracting by 8. Negative 8 plus 8 makes 0. I'm left with 12 is less than 2x, which is less than or equal to 18. As our last step, again, we want to get 2x by itself, so I'm going to undo multiplying by 2 by dividing by 2 on all three sides. 2 divided by 2 makes 1. 12 divided by 2 makes 6, is less than x, is less than or equal to 9. If I'm putting this on a number line, that means I have an open circle on the 6, a closed circle on the 9, and the x is physically in between. So from 6 to 9, including the 9, not including the 6, and that would be my final answer. Of course, I forgot to do the interval notation over here. What do you think the interval notation would be? Similar idea, you do 1/2 to 2, but this time the 2 gets a parenthesis and the 1/2 gets a bracket, because the closed circle means a bracket on the 1/2, open circle means a parenthesis on the 2. What if you have something like this? So here I would say that this inequality is better to break up into two inequalities for two reasons. First of all, these inequality symbols are facing the opposite direction that we're used to doing for and statements, which means they're not like the friendliest to work on all three sides. Secondly, since I have x's in all three parts of this equation, that gets very unwieldy very quickly to work with all three parts. I really only recommend working with all three parts if your x's are only in the middle and you just have numbers on the other side. Here, I would actually split this into two inequalities. So you have one inequality, that's this first one. So we have 3 plus x is greater than 7x minus 2, and we have the second inequality. So they share the middle. 7x minus 2 is greater than 5x minus 10. So I just split it into two where they share the middle there. And then I would just solve both, and since it's an and statement, you're looking for the overlap between the two. So I'm going to pause this video, and I want you to go ahead and solve both of these inequalities yourself, and then come back. Welcome back. All right, so let's go ahead and solve both of these. So I want to move all x's to the left-hand side if I want to be nice to myself. So I want to move this 7x over by subtracting 7x on both sides. 7x minus x gets me 0x there. 3 minus 6x, because 1x minus 7x gets me 6x, is greater than negative 2. Then again, my goal is to get x by itself, so I'm going to undo addition subtraction next by subtracting 3 to both sides. 3 minus 3 gets me 0. Negative 6x is greater than negative 5. Then I again want to get x by itself, so I'm going to undo multiplying by -6 by dividing by -6 on both sides. -6 divided by -6 makes 1, and I'm left with x is less than positive 5/6. So I'm going to start graphing this on a number line, and keeping in mind that I want to find their overlap, I'm just going to start the sketch with an open circle on the 5/6 and indicate I want stuff to the left, but I don't really know how far left I want to go just yet. For the next one, similar idea, I'm going to move all my x's to the left. So I'm going to move this 5x over by undoing adding a positive 5x by subtracting 5x to both sides. 5x minus 5x makes 0. 7x minus 5x makes positive 2x. Minus 2 is greater than -10. Then I want to undo subtracting 2 by adding 2 to both sides. -2 plus 2 makes 0. 2x is greater than -8. And as my last step, I want to undo multiplying by positive 2 by dividing by positive 2 on both sides. 2 divided by 2 makes 1. X is greater than -4. So if I'm plotting that, I have a -4 here. Is strictly greater, so it is open circle, and I'm shading to the right, so it looks like their overlap is right here in the middle. In interval notation, that's -4 to 5/6 parentheses on both because neither are included. Or if I'm turning this into a compound inequality and inequality notation, I could just write an and statement in between them, call it a day. Or if I'm going to combine this into a three-sided inequality, then I need to flip the lower half around to make -4 is less than x, equivalent to x is greater than -4, which is less than 5/6. Both of those would be correct and statements. Please reach out to your professor if you have further questions, and you also have a textbook, so I encourage you to look at that for more examples as well.